So it's a real pleasure to have Lenny Susskind here from Stanford. Lenny is one of the deepest thinkers in quantum gravity. He's one of the fathers of string theory. My colleague Raphael Busso puts it this way. He says Lenny put the string in string theory. So he. I won't say too much here, but let me just say that Lenny has this irresistible clarity with which he presents his work, and maybe this is one of the qualities that's led him to he's actually one of the people who has steered the field, and so. I'm really looking forward to hearing what Lenny has to say about quantum gravity and the quantum extended Church-Turing thesis. So, looking forward to it. Lenny, to you.
Good. So now I can share my screen.
Yes, please do.
All right, let's try that. You won't be able to see me, I think. My setup doesn't allow that, but I don't think you'll be losing too much that way. Start broadcast. Can you see that?
Yes.
All right, let me start. My computer a little bit. I see you on the corner. Do you see me?
I can see you. Yeah,
can
I
or
can
cannot?
Can, yes.
You can see me. Oh, okay. So somehow I didn't think you could. I think you're going to wind up seeing the ceiling mostly. Okay. Those of you who know me know, of course, that I am, first of all, 82 years old. Second of all, I am not a complexity theorist. I was pretty much about 73 years old before I even began to start to think about it. And at my age, you don't learn things easily and quickly. So that's just by way of disclaimer. It's also a true fact. So I'm going to be talking about things which, quite honestly, I know very little about. Complexity theory. But in particular, I'll talk about the Church-Turing thesis, the various versions of the Church-Turing thesis. The Church-Turing theses, what are they? Are they computer science? Are they physics? Are they mathematics? Are they philosophy? I suppose in some sense they're all of them, but whatever it is, they are what they are, and they form a kind of interesting set of guidelines for thinking about the connection between information, between computer science and physics. And I think there's a great deal of value in exploring the connections, even if the precise version of these theses is not completely well known. And I think it's not completely well known. But let's begin. Let me just outline what are the various theses that we're talking about. Probably most of you know this better than I do. There's the original Church-Turing thesis. Anything that can be computed by nature can be computed by a Turing machine. I'm not at all sure this is the way either of those people said it, but that's what it comes down to. Anything that can be computed by a natural process can be computed by a Turing machine. This idea is closely connected to Wigner's puzzling question, what is it that makes mathematics so effective in studying the laws of nature? And the answer is, of course, the laws of nature are mathematical. Well, if mathematics is by definition computation, not all mathematicians will agree that it is computation, but at least some mathematicians would consider mathematics to be basically computation. And the laws of physics are mathematical, then it pretty much follows that, that anything that can be computed by nature can be computed by a Turing machine. So is it true? I think it's true. Is it interesting? I think it's interesting. Is it a tautology? Maybe, but it's one of these interesting tautologies. Next, we come to the extended Church-Turing thesis. anything that can be computed efficiently. Efficiently, I take to mean in less than exponential time or less than exponential number of steps. Anything, well, perhaps a polynomial number of steps, anything that can be computed efficiently by nature can be computed efficiently by a Turing machine. Now, this is a very interesting example because it's known to be false, or at least believed to be false. There's nothing like having something which turns out to be false to convince yourself that it had some, that it actually had some meaning, and that it can be refuted. Why is it false? It's false because we think that quantum computers can compute things that could not be, or that quantum mechanics, because of quantum mechanics, nature can compute things efficiently that Turing machine could not, a classical Turing machine. That led to what is called the quantum extended Church-Turing thesis. And that was a simple elevation of the idea from classical physics to quantum mechanics. And it said that anything that can be computed efficiently by nature can be computed efficiently by a quantum computer. Now, is this true? Most, I think, people would say, yes, most people never heard of it, but most probably people in the audience here would say, yes, it's true, probably true. I have one question about it. It's not so obvious to me that quantum field theory, because of all of its infinities and because of all of its subtleties, cannot in principle compute things which could not be computed on by a quantum computer, by a conventional quantum computer. It comes down to the question of whether a quantum field theory can be simulated by qubits. If a quantum field theory really cannot be can be simulated by qubits, then you might wonder whether the quantum field theory can do things that a system of qubits can't. But I'm going to leave that out now. I'm not going to get into that, although I think it is an interesting question. Can an arbitrary quantum field theory be simulated, quantum simulated, by a system of qubits? Okay, but we're now undergoing a paradigm shift. In fact, I would say that we can judge the revolutionary character of a paradigm shift in physics by how much it makes us rethink the Church-Turing theses. And we are undergoing a paradigm shift in physics now. The quantum gravity shift, it's full of surprising ideas, like that the horizon area is equal to entropy, the holographic principle, something called ER equals EPR, which I'll mention a little bit later. Volume equals complexity, spatial volume equals complexity, all sorts of surprising ideas. And in my view, it would be quite surprising if this paradigm shift did not make us rethink, to some extent, the quantum extended Church-Turing thesis. Can you excuse me for a moment while I shut my door? We're getting a little bit of noise in here, and I want to shut my door to keep the noise from coming in. Hold on, be right back in a second. Okay. All right, the context of my discussion now is going to be very conventional from the point of view of computation and so forth. We're going to be thinking about qubits, universal circuits, k-local gates, gates which are composed out of a small number of qubits at a time, k of them at a time, where k is much smaller than the size of the computer. We will think about fast scrambling, or at least I will use some of the concepts of fast scrambling. What is fast scrambling? Fast scrambling is just the process by which, if you were to add a qubit to a ongoing computation in a computer, if the computation was governed by universal laws, and if it was in particular, if the quantum computer was behaving chaotically, it's just a question of how long it would take for that qubit to be thoroughly absorbed, information theoretically, into the guts of the quantum computer, how long it would take for it to become very difficult to extract back out. The scrambling time is called T star, and it's typically of order logarithm of the number of qubits. I won't using that very much, but I just want to mention it. Complexity evolution is an important idea in what I'll be talking about. I'm not going to talk about it at great length. You can find discussions of it in various places that I've written, in particular my Princeton lectures of a couple of years ago on connection between black holes and complexity. Complexity evolution means if you start with a simple state, uncomplex, by complexity, of course, I mean circuit complexity. Circuit complexity is how many steps, how many gates does it take in order to, what's the minimum number of gates that it takes in order to accomplish whatever it is you're trying to accomplish. Complexity evolution means that if you start with a simple state, it will simply get more complex. That's more or less obvious up to some point. And the ideas of circuit complexity that I have drawn on are, first of all, just basic circuit complexity, Nielsen's geometric ideas of converting questions of complexity into differential geometry, a version of Nielsen's idea, which is due to Brown and myself. But I don't think we need to get into that too much. The main important thing is there is a concept of complexity, and it is fairly universal, or that's an assumption, that it's fairly universal, all these different ways of thinking about complexity, as long as the complexity is not too small, will pretty much give you the same complexity. If that were not true, then complexity would not be a very interesting idea. Some concept of universality. All right, now, another fact, the maximal complexity of a system of n qubits is exponential in n. 4 to the n, I'm talking about now the complexity of unitary operators. We could talk about state complexity, then it would be 2 to the n. The maximal complexity of a circuit or maximal complexity of a state is exponential in n. And once you reach that exponential value, the complexity stops increasing. You can continue to run the circuit, run more and more gates, but you will always find that that same final state could be accomplished with fewer gates than you used. You never need more than 4 to the n. I'll also assume that the complexity grows according to a particular rule, namely that it grows linearly for a long period of time, linearly and proportional to the number of qubits. And then it grows until it reaches the maximum and then stops growing. These are all fairly familiar ideas. To what extent they're proved or not proved, I won't get into here. They are assumptions. Finally, black holes are fairly conventional, chaotic quantum systems for which all of this stuff applies. All right, now I want to come to an issue that was raised in 2013 by a group known as the AMPS group, Almari, Marolf, Bolchinski, and Sully. And I'm not going to get deeply into the issue of firewalls, but I'm just going to write down one statement that was made in the context of the AMPS firewall paradox. And only one statement. The claim was that the generic quantum states of a black hole have firewalls. Now, a firewall to me doesn't really mean a wall of fire. It means a firewall in the sense of an obstruction to information entering the black hole, entering behind the horizon of the black hole. The black hole is a firewall in the sense of an obstruction to information entering it. That was the claim, generic quantum states. But what did they mean? The important issue here is, what did they mean by a generic state? I'm only using the AMP story here to pull out the word generic. What is the nature, what is the meaning of generic quantum state? Is it a state which is thermalized, in other words, which has run long enough chaotically to behave thermally? Well, that takes a very short amount of time. Thermal equilibrium is established for a system very rapidly, certainly in polynomial time, more likely time of order 1. Is it scrambled? Scrambled is a fancier version of thermalized, which takes a little bit longer, in which information is really absorbed into the system in a way that's very difficult to extract. Is it scrambled? Is it thermalized? The AMPS people assumed that a thermalized or scrambled state was generic quantum state. Well, then comes the question, are black holes in nature generic? I'm going to now explain to you why a generic quantum state is very, very far from what is ordinarily meant by thermal or scrambled or anything that can be produced in a reasonable length of time. Here's an example of hidden order that's present in a quantum system for a very, very long period of time. Let's see. Imagine a quantum state of a chaotic system which is evolving in time. Here's the standard rule for the evolution of a quantum state in time. Let's suppose the psi sub i's here are real numbers just for simplicity. And let's also suppose that the energy spectrum is bounded from below, and in fact bounded from below at 0. Then these phases here are all that vary with time. They're phases, they move on a unit circle. At time t equals 0, they're all at the same point, namely 1. And as the system evolves, the individual phases start winding around the circle. The velocity is proportional, velocity is the energy of the particular state. And so they all like a snake, like a worm, they start to spread out over here. And it doesn't take very long for the first leading edge of the worm over here to completely circumnavigate the circle. Why? Because leading edge here is determined by the highest energy state. It takes a small amount of time to go around, and then it keeps going around and it keeps going around. Now, to show you what this hidden order is, let's consider neighboring states. By neighboring states, I mean they have neighboring energies. Neighboring meaning closest, nearest neighbor in energy. What happens to the distance between them as time goes on? Well, of course, it grows, but it grows for a very long time and remains small for a very long time because the energy levels are so close. This means that, for example, if you were to look after a fair amount of time at the sequence of phases here, 1, 2, 3, the first one, the second one, the third one, the fourth one, and so forth, they would form a sequence which would be very recognizable. You would, after a time, you would see perhaps 1 over here, 2 over here, 3 over here. Now, of course, there may be things in between. If the worm had traveled all around the circle here a few times, there will be things in between, but you will still find that 1 is close to 2, 2 is close to 3, 3 is close to 4, and so forth for a long time. How long a time? The time would be the time that it would take for 2 neighboring energy levels, 1 and 2, to separate by something like the circumference of the circle, 2 pi, a small fraction of 2 pi, but a small fraction of order 1. Once that happens, the ordering of the levels gets all mixed up on here. 1, 4, 2, 5, 3, and so forth. In other words, after a period, the sequence or the order, and I mean now the order of levels gets all mixed up and difficult to, very difficult to become pseudo-random, if you like. How long does that take? It takes a time of order e to the entropy of the system. That's because the neighboring energy levels have a distance between them, e to the minus the entropy. And so it takes a time of order e to the entropy for this order, this recognizable order, to disappear. This is long, long, long beyond the time that it takes to thermalize. And so there is some measure of randomness that grows long past thermalization. Or you could say it the other way. There is some measure of order which decreases or which decays for times long past thermalization. Genericity, true genericity of a quantum state, only occurs after exponentially long times. So what Amps was thinking, Amari and company, that a state became generic after a thermalization time or a scrambling time is not at all true. The state still has a great deal of order. And that was part of the resolution of this firewall paradox. I don't want to get into the firewall paradox. I simply wanted to point out that there is hidden order in quantum states that lasts for a very long time, exponentially long. All right, let's move on to something else now, which is going to come up. The ER equals EPR idea. ER here stands for Einstein-Rosen bridge, Einstein-Rosen wormhole, otherwise known as a wormhole. EPR, well, that you're probably very familiar with. That's Einstein, Podolsky, and Rosen, and it stands for entanglement. Incidentally, in the original EPR paper, I think EPR actually stood for elements of physical reality. But we all recognize it as Einstein, Podolsky, and Rosen. And I simply want to just quickly go through the idea that in some sense, these two ideas are the same. There was, this of course does not appear in the 1935 papers of Einstein, Rosen, Podolsky, and so forth. There was no connection whatever made between entanglement and wormholes. This is something that came later, but let's just discuss what it means. The bent over sheet here, that's just supposed to be space, and I bent it over just for convenience. You'll see what I mean in a moment. Let's suppose in one region, we have a bunch of particles. In another region very far away, we have another set of particles, a dust cloud, a pair of dust clouds of particles. And these particles are allowed to collapse into black holes. Incidentally, these particles have never seen each other. They've never talked to each other. One group is off in Alpha Centauri. The other is in Brooklyn, I don't know where. And they've never seen each other. They've never spoken to each other. They've never interacted with each other. The particles may have interacted with each other, but the ones on the top have not interacted with the ones on the bottom. And then they are allowed to undergo gravitational collapse to make black holes. This is my picture of a black hole. Not important that it be realistic. They collapse to form two black holes. The two black holes are completely disconnected from each other and have no particular relationship to each other. Now let's compare that with another thing. The next thing is, let's start with entangled pairs. The green lines here just indicate maximal entanglement. Maximal entanglement, let's say, between the spins or between anything, any degrees of freedom describing the particles. Now, there's no way that you can have that kind of entanglement unless at some point the particles did interact with each other. So what you should imagine is that they all started out near each other, entangled, and then separated into two subsets of entangled particles. Now let the entangled particles undergo gravitational collapse. Gravitational collapse of this subset and gravitational collapse of that subset. That again creates two black holes, but now according to the ER equals EPR hypothesis, they create a pair of black holes with a wormhole connecting them. That's the ER equals EPR hypothesis. It's well tested. I was rather surprised when Juan Maldacena and I first put this idea out that people accepted it as quickly as they did, but they did, and it's now a well-recognized part of quantum gravity, if you like, ER equals EPR. As I said, what it means is if you create a pair of black holes by collapsing entangled particles, the black holes will have spatial connectivity between here and here. they will be connected by a wormhole. Now I'm going to jump. Well, I'm not really jumping. I'm just describing this wormhole here in another way by a Penrose diagram. I am aware of the fact that a fraction of the audience doesn't know very much about gravity and doesn't know very much about general relativity or black holes. I'm going to ignore that fact, but I'm going to try to explain things in a way which is reasonably self-contained so that hopefully you'll get the idea of how a Penrose diagram works. The left side, incidentally, here my two black holes are one on top of the other. They're related vertically. Here they're related horizontally. I think I can fix this. Just a moment, let me fix this. There, now my black holes are related horizontally. Left black hole, right black hole. Entangled. This is the Penrose diagram that goes with that particular kind of pair of black holes, which are entangled and therefore connected by a wormhole. The left side, this is the exterior of the left black hole, the region out here, the exterior. Here's the exterior of the right black hole out here. And here is the interior of the black hole. In fact, it's the wormhole itself. The wormhole is the region in between. Here's the wormhole. Forget the bottom half of the diagram for a moment. And the various things you need to know about this is the top edge of the diagram is the singularity. The left edge over here and the right edge, the left edge and the right edge correspond to the location of the holographic degrees of freedom describing these black holes. And now you can ask, what about the region outside these two black holes in which you can imagine moving around from one to the other? Well, that's not drawn here, but you can think of it as the Penrose diagram being embedded in a bigger space, which allows you to move around the long way. The wormhole is moving the short way. It goes through here. And you can also go the long way. All right, now I'm quite aware that this is, at best, very hazy for those who've never studied black holes. But let's keep going. Let's see what all this means. First of all, the exterior of the black holes are in fact completely static. This doesn't look static here. It looks like, it looks like this time-dependent. These are time slices here. Time slices look like this. Constant radius from the center of the black hole looks like this. And the diagram is drawn in such a way, the most important thing is that light rays move on 45-degree angles. That's the most important thing. Okay. For better or worse, I will assume that you have some rough idea of what this picture is representing. Again, another important thing is that what's going on in the exterior of the black holes is completely static. This point is like this point, is like this point, is like this point, is like this point. Completely static with no time evolution going on from the point of view of the exterior observer over here or the exterior observer over here. All right, here's a picture of somebody jumping into the black hole. The purple line here, that's the trajectory of Bob. Bob is always the fellow who jumps into the black hole from the right side. Bob jumps in, eventually hits the singularity, is a bit suicidal to do so, crosses the horizon over here. Now, in what sense is this the horizon over here? It's clear that anybody who passes this point cannot get out without exceeding the speed of light. Cannot get out and escape back out to the exterior regions. That's what the horizon is, a point of no return. Once you've crossed it, you can't get back out. So Bob, when he crosses the horizon, is inevitably doomed to hit the singularity. All right, one thing that can happen with these entangled black holes, remember, one is off on Alpha Centauri, the other is in Brooklyn. Alice on her side and Bob on his side can each jump into their black holes. Let's go back to the earlier picture. That means Alice jumping in from here, Bob jumping in from here. And as you can see, it's potentially possible for them to meet in a very short amount of time, even if the black holes are very, very far apart. Alice and Bob can meet, shake hands, do whatever it is that Alice and Bob do. However, as I said, it's somewhat suicidal. Romeo and Juliet will soon expire at the singularity. But what is impossible is for a signal, in particular, a signal that they met over here or any other signal that began behind the horizon, to get out into the exterior region. No, classically, this is a classical statement, no message can escape from behind the horizon. This is the behind the horizon region. Okay, that's really all we need to know. Well, no, it's not all we need to know. We need to know a little more. One other point, as I said, the exterior regions here are static. In fact, they are in thermal equilibrium. The fact that the two sides are entangled means that if you integrate it out, in other words, if you traced over one side, the other side would be in some non-trivial density matrix. In this setup, the density matrix of each side, when traced out over the other side, is perfectly thermal and, in fact, is in thermal equilibrium. Now let's jump ahead to the next observation. I told you that the exterior regions are perfectly static, but if you look at this diagram, it's completely obvious that the interior region behind the horizons are not at all static. In fact, that region is growing with time. And its volume is growing linearly with time. Something is going on in this system here, which is growing linearly with time, even though from the point of view of the exterior of the black holes, the systems are in perfect thermal equilibrium. Nevertheless, something is growing, and it's possible to argue reasonably that this growth will go on for a very long, exponentially long period of time. We don't need to think about these two-sided entangled black holes to make the point. For those who recognize the Penrose diagram for a black hole formed by the collapse of a star, this is the material of the star. It collapses, eventually forms a singularity, and here's the horizon. If you recognize it, this will mean something to you. We follow the horizon. The horizon grows. According to the rules of quantum gravity, the growth of the horizon means that the entropy of the black hole or the entropy of the configuration is growing. It's growing because the star is collapsing, and as it collapses, the entropy grows, but it stops growing right over here. At this point, the area of the horizon simply becomes constant, and the entropy of the black hole stops growing. It becomes static, perfectly static, and in thermal equilibrium. On the other hand, if you look at this Penrose diagram, you will see that the region behind the horizon is growing. It's growing, and it grows for a very long time. Something grows linearly with time long after thermal equilibrium is established. That, of course, should remind you of what I said earlier, that there's a subtle kind of hidden order in quantum systems that can evolve for long, long times past thermal equilibrium. Incidentally, this idea was something of a shock to most physicists, that thermal equilibrium is not the end of the line for quantum evolution. whatever it is, whatever represents, whatever quantum thing represents this growth here, it is very hard to feel from the outside. I'm using the term feel now in a sense that was, to my knowledge, coined by Adam Bouland, Bill Fefferman, and Umesh. We'll come back to what feel means in a little while. But it's very difficult to feel in the sense that what's going on out here is practically in perfect thermal equilibrium, and very hard to detect this very fine-spun thing, this fine-spun order, this unfeelable order. And I'll come to what unfeelable means in a moment. But what is this quantity? What is this quantity which continues to grow? My answer was that about the only thing that it could be is quantum circuit complexity. That's quantum circuit complexity was the obvious candidate for something which grows long, long after thermal equilibrium. It's a very fine-spun quantity, difficult to detect, but it exists. It exists and it grows. If we were to look at the evolution of quantum complexity, now this is something of a conjecture. Some parts of it have been proved. Some versions of it have been proved in various kinds of toy models. The complexity as a function of time grows linearly. As you lay down gates, the complexity simply grows linearly. The number of gates it took to get to that state grows linearly until it saturates. It saturates when the complexity reaches the maximum possible value, and then it simply is constant with small fluctuations. That still is something of a conjecture, but I think at least in part it has been proved for some simple systems, and I will assume it, of course. If you were to take a microscope, not a microscope, a magnifying glass, and lay it down over here, you would find that the thermalization time, the conventional thermalization time, was a tiny, tiny fraction of the time spent during which the complexity was growing. I would say that any state, it doesn't matter whether it's a black hole or a quantum computer or whatever it happens to be, if it's a chaotic system, will follow something like this, will follow a complexity evolution, something like this, where most of the time, most of the observable time is spent during this period of increase. It takes very, very long for it to reach the generic behavior, which does in fact last for a much longer time. But generic is up here, linearly growing is over here, and anything you can make in the laboratory or in astronomy or any other reasonable situation will lie somewheres along this growing region. So black holes in nature would be expected to be in this growing region here. Okay, when I put this idea out that the thing that was growing in the interior of a black hole was quantum complexity, it met with two pretty much distinct reactions. From the quantum gravity community, I'll call it the IFQ, the it from qubit community, everybody seemed happy with that. Okay, complexity equals volume of the wormhole. There was very little resistance to it. People started making calculations all over the place. Some of the calculations were very interesting. Some calculations of what? Calculation of the growth of the volume of the interior of black holes. But didn't ask very hard questions about this. Largely just accepted it. I was surprised. On the other hand, from the complexity theoretic community, the reaction was different. Although very polite, it basically was, no, you can't be right. That must be wrong. That's crazy. At least two of the people that I remember reacting, again, politely, but reacting that way was Scott Aaronson and Adam Bouland. I told this story at one point to Umesh very early on, and Umesh is very, very polite and kind and generous, but I could see in his eye skepticism. Why the skepticism? And the reason is because quantum complexity is unfeelable. That was a term, as I said, that was coined by Bouland, Fefferman. Umesh, am I right that term was coined by you guys? Umesh, are you there?
Yeah. Hi, yeah, that's true, right.
Yeah, and at first I thought the word unfeelable was a little bit too peculiar, but I've come to think that unfeelable is exactly the right word to describe the fine-spun nature of quantum complexity. So what does it mean that the quantum complexity is unfeelable? Well, first of all, it means that it's uncomputable and unmeasurable. Well, not quite uncomputable. When I mean uncomputable here, I mean uncomputable in the practical sense, that it's exponentially difficult. I'll come to that in a moment, but that in practice, that it is uncomputable and unmeasurable, impossible, not quite impossible, but almost impossible to tell the difference between very moderate amounts of complexity and exponentially large amounts of complexity. It's unfeelable, it's uncalculable, it's unmeasurable. And here's an example of the sense in which that's true. Let's suppose I gave you a quantum state. Now, by saying I gave you a quantum state, I literally mean I give you a system in that quantum state. I may even give you the system and a polynomial number of replicas of the system. And I promise you that A or B is true. A, the complexity of the state psi is a certain number C, which we can assume is polynomial for the moment, polynomial in the number of qubits. Modest, even small. Well, and numerically large, but small by compared with the maximal complexity. Or B, the complexity of psi is maximal, that the state psi is a completely generic, maximally complex state. And I tell you, it's one or the other. What is the computational complexity of distinguishing A from B? This is not asking what the complexity of A or B is. It's asking what is the complexity of distinguishing A from B. I call that the complexity of complexity, the complexity of determining how complex a state is. I called it CC. Well, it turns out there's only one procedure for measuring the complexity of a state, or in this case, of distinguishing A from B. And it basically consists, all right, the circle here is supposed to be the space of states, the unit ball, the unit sphere, space of states of the n qubit system. Technically, it's CP2 to the n minus 1 or something, but it's basically a sphere. This is the space of states. Here's a simple state. Let's say a completely unentangled state. Here's the state psi in question. How do you compute, or how do you determine what the complexity is? And the answer is basically you try all possible circuits. Circuit here, here's a gate, here's another gate, here's another gate, here's another gate. You simply try all possible circuits, sequence of gates, of length c and see whether you hit the target state. The shortest such sequence, there are many such sequences, in fact, eventually almost anything will hit C. The shortest such sequence is the complexity of C here, but in order to test what the complexity is, there's really no alternative than basically trying all possible circuits until you hit that point. Until you hit that point and check that it was the minimal one. How many such circuits are there, or how many such trajectories are there, sequences of gates of length C? The answer is e to the C. The number of trajectories, of number of circuits of length C, length meaning the number of gates in them, is e to the C. And so what that tells us is that the complexity of complexity, the complexity of knowing the complexity, is itself exponential in C. Now, C could be relatively small. C could be polynomial. It could be 1,000, or it could be 1,000,000. That's small by comparison with anything we're really interested in. E to the C is not small. So this is the sense in which determining the complexity, or the complexity is unfeelable. You can't efficiently calculate it, even if it's relatively small. To calculate it is a very, very difficult, exponentially difficult problem. And you can't efficiently measure it. If that's true, if it is that fine spun, that unfeelable, how can it possibly be related to anything physical? That, I think, was the complaint that the people who really knew about complexity had about the idea that complexity could be representing the physical property of the size of the interior of the black hole. It led various people. I know that Scott used the term, or something like it. Adam used the term. It must be some sort of pseudo complexity. It can't be genuine complexity that is really measuring the size of the interior of the black hole. It must be some pseudo complexity, something that behaves like complexity, but is not really complexity, something more feelable. My answer to that was, don't be so surprised that, be so surprised by the unfeelability of whatever it is that's determining the size of the interior of the black hole. The interior of the black hole is also very unfeelable from the outside. Remember that all during this growth of the interior of the black hole, the outsides of the black hole, the outsides of the wormhole, are in perfect thermal equilibrium, or close to perfect thermal equilibrium, and it is very difficult to detect what's going on the interior. So really, there's no real contradiction there. Both are very unfeelable. That was my answer. I don't think it was completely satisfactory, and it certainly didn't satisfy the complexity theorists. I can stop here for questions too, if anybody wants to. Okay, I'll go on. Come on the scene, Bouland, Fefferman, and Vazirani, who I believe at the time when they started the project were trying to demonstrate that complexity could not be what's going on in the interior of the black hole, for all the reasons that I said. They invented a particular protocol, which goes something like this. Here's your two-sided black hole. I don't think they were terribly specific about whether they're talking about a two-sided black hole, two black holes, or one black hole. This wasn't terribly important. And let's imagine now waiting. Here's time t equals 0. Let's see, here is time t equals 0. Whoops, right over here when the black hole was created. It evolves for a period of time upward, and at some later time, we are given the state of the black hole. Somebody's given the state of the black hole, and what are they asked? They are asked how big, given the state, they are asked to determine how big at that time the wormhole is. Okay, now in general, that is not too hard because you can evolve, if you know the Hamiltonian, you can evolve the system backward in time for a period, see how long it takes for you to get back to the simple state, to the simple initial state. And if you know how long it took, then you know how big the wormhole is. Well, Bouland, Fefferman, and Vazirani wanted to avoid that situation. And so they said, let's throw in randomly or pseudo-randomly a collection of perturbations. The first perturbation at this time, wait a scrambling time, perturb it again. Wait a scrambling time, perturb it again. Those perturbations send in waves or particles or whatever. And we're going to do this somewhat randomly in the following sense. The perturbation that we send in could be one of two possibilities. Let's call them U and V. But we're going to arrange them randomly, and we're not going to tell, we're going to keep secret what the sequence of perturbations were. We'll keep that secret in our pocket and not give it to Bob and Alice. Bob and Alice later are going to be asked to reconstruct from the state over here what the length of the wormhole is. That's a hard problem. That's a hard problem in the sense that if you don't have the ability to run the system backward, you simply have to learn what it is by using the dictionary connecting the quantum mechanics to gravity. How hard is that? Well, if there are L random perturbations, then the answer is from a complexity point of view, the complexity of knowing the complexity of the state is again exponential of order 2 to the L or bigger. In other words, even if L is modest, even if the system has only been allowed to evolve for a relatively short amount of time, it is still extremely hard to tell what the output is from a completely maximally random state. That was the Vazirani construction, and it indicated just how hard it is to reconstruct information about the interior of a black hole from knowledge or from being presented with the actual quantum states. Another way to say it is whatever the volume is here, it is very unfeelable from the outside. Okay, now what the authors then said is surely the volume of the wormhole is feelable. We've proved that the complexity of the state is very unfeelable, but surely the volume of the wormhole is feelable. Well, no, it's actually not, but for a reason which is somewhat irrelevant. The reason that it's not feelable is because once it gets a little bit too late, no observer who can observe a point over here can also observe a point over here or a point over here. It's not really possible to measure the entire, for any given observer to measure the whole length of the wormhole, but that's not really relevant. That's not relevant to the way that Umesh and company phrased the argument. Here's what they said. Their argument was more subtle and got around this issue that you can't really measure the volume of the wormhole. Let's assume that the dictionary relating the quantum mechanics of the boundary of the black hole, the ADS-CFT dictionary. It's the quantum gravity dictionary. Let's assume that it's efficient. Efficient meaning that if you're given the state psi in a sub-exponential time, sub-exponential number of steps, you can predict what the metric is in the interior of the black hole. Given psi, you can then calculate efficiently under the assumption that the dictionary is efficient. You can compute the volume of the wormhole. Here it is. Given the state here, and given that the dictionary between exterior and interior is efficient, you can calculate the volume of that wormhole just by integrating the metric. And that's not very hard. Integrating it up numerically or however you want to do it. And so it would seem that the volume of the interior is feelable and easy to compute if the dictionary is simple, if the dictionary is efficient. What it would mean for the dictionary to not be efficient is almost that it's useless. If the dictionary is not efficient, it's practically useless. It would mean that to make any prediction about the interior is an exponentially difficult problem, knowing about the quantum state of the system. All right, but if complexity and the volume of the interior are really the same thing, then there is a problem. C, the complexity is unfeelable for the reasons that I said, but the volume appears to be feelable. How can they be the same thing? The conclusion is one of two things. Either the quantum extended Church-Turing thesis is wrong in this context. In other words, that there is a physical way of measuring or determining or computing, they're all the same thing in a quantum context, the volume of the interior. That the volume of the interior is expected to be feelable and easy to compute. On the other hand, the quantum complexity theory would tell us that it's very, very hard to compute the complexity. That's a mismatch. Either the quantum ECTT is wrong in this context, or the dictionary must be exponentially complex itself, even for relatively uncomplex psi. I believe this is correct. I believe the argument is correct, but I would like to try to do better. I see I'm running out of time, but I'll try to get to the point as quickly as possible. Can we do better than BFV? And doing better here would mean that we construct a situation where Bob can actually solve an exponentially hard problem in a short time by actually jumping into the black hole. That was not possible in the case of the volume of the interior, because it just was not possible to measure the whole volume of the interior. But I think the answer is yes, we can construct an example. This is an example of a problem that I think can be solved by jumping into the black hole, whereas other methods would be exponentially difficult. Here's the setup. Umesh, do I have a few more minutes?
Oh, yes. Yeah, that's fine.
Oh, good. Excellent. Excellent. Good. All right. Here's what we're going to do. We're not going to just send in the signals that Umesh and company invented to sort of blur what's going on between t equals 0 and the time we actually do our measurements, blur it or randomize it. We're going to do something first before that. We're going to put in a signal very early on. Now, put the signal in very early on. What we have to imagine is that we can run our system backward, run our black hole, or run our simulating system backward for a time, apply a perturbation, and then run it forward again. That would correspond to putting in a perturbation in the past. And let's suppose that perturbation is one of two types. They could be distinguished, for example. This could be a photon being sent into the wormhole, and the photon could have one of two polarization states, either A or B. Or it could be an electron or a muon, or whatever we like, some distinction between A and B, which is quite feelable, easy to tell the difference between an electron and muon. But now what happens is this perturbation starts to fall into the black hole. As it falls into the black hole, it is blue shifted. This is simply the statement that its energy increases as it falls into the black hole. And by the time it gets to the horizon, its energy is huge. Its energy is huge, and this has become a very dangerous shock wave for anybody who would fall in at this time over here. The perturbation falls in, becomes a shock wave, and then continues on its way through the wormhole, and eventually gets to the singularity. Of course, as it comes up out of the black hole, or as it comes back up out, it loses energy. So it goes in, becomes a very intense shock wave, and then climbs back out. Eventually hits the singularity over here. It doesn't get to the outside, but by the time it gets over here, it's fairly benign, and its energy is very low. Okay, what is the problem that we want to solve? We want, from the point of view of knowing the quantum state at a later time, being handed this quantum state at a later time, Bob's, or is it Alice, I'm not sure, or maybe jointly, they're going to try to figure out whether we sent in A or B. That's the problem, A or B. Well, in this context, A or B, in particular, if we've randomized the state by sending in these waves over here, A or B will be very unfeelable from the outside. Why? Because the sequence of perturbations here makes the state quite indistinguishable from a maximally complex state. In a maximally complex state, you certainly can't tell the difference between whether you sent in A or B easily. So it's expected that this problem, I won't get deeply into it, but it's expected that this problem is a hard problem. Hard problem in the sense that it's exponentially difficult in the number of perturbations that were created, whose only purpose was to obscure and make the problem difficult. Okay, so that's the problem. How can it be solved? Here I've sort of focused in on the corner over here, what's going on. The shock wave comes in, starts to lose energy, and as it comes in, it becomes rather benign. In fact, it turns back into a photon, a low energy photon, for example, of either A or B type. In fact, it remembers what type was sent in over here. It comes out over here, either A or B. And Bob is now going to solve the problem by simply jumping into the black hole. He'll jump into the black hole, very easily detect whether the green particle is A or B, and therefore will have solved what is a very difficult computational problem by simply jumping into the black hole. Sounds a bit crazy, but and this is essentially the BFV idea, but constructed in such a way that an observer can really jump in and determine the answer to the problem. So Bob easily beats the quantum extended Church-Turing thesis, but of course at the cost of being rather suicidal and at the cost of not being able to ever get the information out. So he has learned what he wanted to learn, but in a sense, it's useless information. at least useless from the outside of the black hole. Here's a quantum circuit which represents basically the same thing I did. The two sides of the quantum circuit are representing the two black holes. They're two entangled quantum computers, if you like, entangled in the thermal field double state. Thermal field double state just means a state of high entanglement. The two quantum computers. Let's not get into the details of the architecture of the quantum computers. And over here, there is a gate. It's not a 2-qubit gate. It's a complicated gate. And it represents going backward, perturbing the system, and going forward again by a sequence of operators. It's just a complicated gate which does the same thing as on this Penrose diagram, running backward, perturbing, and going forward. I just illustrate this to say there is a quantum circuit version of this. What about Bob jumping into the black hole? Bob jumping into the black hole could simply be Bob, who is, after all, a bunch of qubits, merging with the quantum computer and then being scrambled into the quantum computer. What the black hole story is telling us is that in some sense, when Bob has merged into the quantum computer here, he can gain knowledge of A versus B that would be very, very hard for somebody who stayed on the outside. We can imagine the following scenario. This is Bob again. Bob doesn't jump in himself. He sends in Bob Prime. Bob Prime is a drone Bob. We send drone Bob in. Drone Bob goes into the interior of the computer, makes whatever measurements, which are not very difficult measurements, and determines A versus B. Or at least that's what the black hole is telling us is possible. He learns A, B very fast. The problem is he can't get the information, Bob Prime can't get the information back out to Bob. So this suggests a version of the quantum, let's call it the quantum gravity extended Church-Turing thesis, that it actually applies only to observers who remain outside the horizon of the black hole and not observers who fall through the horizon. In other words, we're accepting the idea, I accept the idea, that Bob can learn this kind of forbidden information at the cost of jumping through the horizon, but that to get that information out to a conventional observer on the outside of the process, Bob who remains outside, that in itself is exponentially difficult. This suggests a new kind of meaning to the horizon of a black hole. The properties of the horizon, the difficulty of getting information out past the horizon once it's inside, is the thing which protects the QGECT. There's another T at the end of this, isn't there? Thesis. It's the properties of the horizon itself which protects Bob on the outside from ever gaining information which would violate the thesis. Okay, that sounds somewhat trivial, but it leads to some basic conjectures. For example, it tells us, or it suggests, that the computational complexity of extracting a certain kind of information from the interior of the black hole is, in this case, at least 2 to the L. We should be able to prove, either in the gravitational context or the computer circuit context, and in particular in the gravitational context, that any protocol which extracts information from the interior of a black hole, in this case, will require a complexity of at least 2 to the L to extract out the information that Bob himself got so easily. Now, there's lots of evidence that something like this is true, that it is that hard to get information out from a black hole. It's not impossible. It is that hard. For example, you can extract out information by letting the black hole evaporate. But there's lots of information, lots of evidence that it is exponentially difficult to extract that information. The question is there a match? Is there a match between what the quantum computation, quantum complexity theory says the difficulty is, and what the application of these various protocols to the gravitational system is? But what I find most interesting is the idea that there are new complexity classes. In particular, a new complexity class that I call JI/poly. J and I stand for jumping into the black hole. It would consist of all problems which can be solved internally in the quantum computer, or better yet, or in the black hole case, all problems which can be solved by Bob by jumping into the black hole efficiently and quickly, but which presumably require exponential effort to extract the information out. You might phrase it this way: a complexity class which involves information or problems which would be easy to solve if you could summon a complexity genie. A complexity genie means a genie which can invoke that genie once. The genie has the capacity in a small amount of time of executing a highly complex operation, an exponentially complex operation. The genie, you can tell the genie what exponentially complex operation to do. The genie can do it quickly, but only once. What are the class of problems which are easy if you can summon a complexity genie, but otherwise extremely difficult? I think that is something like that is the complexity class of problems which can be solved by Bob by jumping through the horizon of the black hole and learning information that is inaccessible from the outside. All of this is closely related to the idea that Bouland, Fefferman, and Vazirani said, namely that the dictionary between the inside and the outside is exponentially difficult. You solve the problem internally in the computer or in the black hole, but then getting it back out is the difficult thing. So I think the AB example here is an existence proof, or at least if it can be done with more precision or enough precision, would be an existence proof that this complexity class is non-empty. The complexity class JI poly, which in computer language would be the complexity class of things which are easy if you can summon a complexity genie, but otherwise hard. Okay, I think I'm finished.
Great. Well, thank you very much for, that was a really stimulating talk. I think there are a few questions from the audience.
By the way, I wanted to say one thing I meant to say.
Yeah.
I did not decide to talk about the subject because you invited me.
Yeah.
I had been thinking about this subject along with Scott and other people for a while, and the fact that you just happened to invite me was more or less accidental.
No, I guessed as much. No, this is fantastic. It's really thought-provoking. I think you have some questions from the audience. maybe we can
Okay.
do a couple of questions before we move on to the panel. I think
should I leave the screen this way, or should I?
Maybe you can, if you can stop sharing, it would be helpful.
I always have.
I just promote. Eli had a question. I think I just unmuted him.
Yes, thank you very much for unmuting me.
Hold on a second. Let me reorganize my computer here. Just give me a second. Okay. All right, now how do I do this? I forget how to do this. Oops.
Okay, and maybe we can have your. Can we start Lenny's?
Wait, the host has asked you to start your video. Okay. Can you see me?
Yes.
Okay. And you can.
We can see the lower half of your. Oh, now we can see you. Great.
Yeah. Okay. All right. The problem is I can't write on the computer if it's tilted vertical. I need it to be horizontal. If it's horizontal, all you get to see is the ceiling in my room. So
yeah, I noticed the ceiling. And by the way, what software were you writing on?
Oh, it's called Notability. It's very good.
Okay, so I have a question. It was a very stimulating talk. Now, it seems to me that in physics there's this idea we don't ask questions for which there's no answer, and anything past the event horizon we're not supposed to know about. So it seems to me that all the pictures that you have drawn that are inside the event horizon are totally optional, and that you could have arrived at the same conclusions without invoking anything past the event horizon.
No.
Do you have any comment on that?
Yeah, I do. The idea that nothing from behind the event horizon can be extracted is a classical idea. It is not thought to be true quantum mechanically. It is just thought to be exponentially difficult. So
I agree with that, but it seems to me that you could have made the same argument without going behind the event horizon. For example, all the photons falling into the event horizon, they get scrambled, they get squished, and then it gets to be a very difficult computation to reconstruct them on their way out. Yeah. Wouldn't that pretty much say the same thing without invoking something inside the event horizon?
Well, the point here is that the curiosity that we're pointing to is that from all that we know about general relativity, quantum mechanics, and their relationship, it appears that an observer willing to jump into the black hole can answer the question easily and quickly. Now, you may or may not find that interesting. Some people think, no, that can't be right. I think it's right. Some people think, well, it could be right, but it's not interesting. I find it interesting. But it also points, as I said, to a complexity class of those problems which can be solved in that way. And I think that complexity class can be translated into quantum computational language, but it involves the existence of what I call the complexity genie. So
right. That part I understand. Thank you.
Yeah. Who are you anyway?
This is Eli Yablonowicz from UC Berkeley.
Okay. All right. Oh, did we meet?
I think we met. We're both the old timers, so we've met at some point.
Yeah, I think we did. Yeah.
Sorry, Seth, did you want to ask a question? You were waving?
No, I was just waving at Eli.
Okay.
Oh, okay, Seth, nice to see you.
I do have some questions for Lenny, which was, by the way, was a super great talk.
Thank you, Seth.
I'm confused about a couple of things. I don't know. Can somebody let me show my screen here? Is that okay?
Okay with me.
If you can keep it short, because we should be moving up to the panel soon. So
okay, good.
We are running a bit late.
Good. First of all, I'd like to some of you may notice this. This is the cover of Scientific American from 2004 by an article that I wrote about black hole quantum computers. So talking about, for people who actually want to look at the actual physics of how many operations you can perform with stuff falling into a black hole, even though it's Scientific American, it's a good article for that. I'm sorry, I shouldn't advertise it in that way, but
I've read it.
My question, I have some questions. So when I was learning, let me see if I can actually share this other thing. So I'm a little confused about a couple of things, which are this. So can you see this right now?
Yes.
I just redrew this is the Penrose diagram for the ER wormhole. It's also the same as the Penrose diagram for the analytic continuation of a black hole, at least this part right here. And I'm just going to draw some lines that I saw Stephen Hawking draw on these when I took his quantum gravity course in 2004. So I have an issue here. I don't know if you can see my pointer, maybe not. But here's Bob outside, and here's Bob's time outside, right here. And then here's Alice over here, and here's her time out there. But the thing is that once you go through the horizon right here, which is this point right here, and this is, of course, the light-like future horizon, but this is what you see as a space, the intersection of your space-like surface in the horizon. So what Bob sees as time going forward is for Alice time going the other way.
No.
So hold it just a second, just let me finish. So when Bob falls into the black hole and goes into this part of the interior of the wormhole, Alice is going into a spatially distinct part of the interior of the wormhole. And so they can't actually meet each other. Can you comment on that? I mean, it doesn't make sense with what Stephen was saying.
No, I mean, look, the black hole isn't that different than ordinary Rindler space.
Yeah, exactly.
Imagine that you drew Rindler space. Yep. Well, there are various kinds of time translation or various notions of time that you can use. You can use the time that you're drawing, which I call boost time. I think everybody calls it boost time or Rindler time.
Yeah.
Runs forward on the right and backward on the left.
Right, like that. I'm just drawing your.
Okay, but there's also just good old Minkowski time, which runs forward on both sides. Now, you get your choice. You can use whatever time variable you like. But if we're really talking about the situation, not of two completely disconnected, non-interacting worlds, but of two black holes which are simply well separated. The example that I gave was particles which were entangled, dragged apart. They started close together. They were dragged apart. They're in the same universe. Time goes forward in all parts of that universe, and then you collapse them to form two black holes. Then the natural timekeeping is for both times to go up.
Okay, good. So that's what I wanted to clarify. So you're saying in the picture you drew, you get two sets of entangled particles. They go way off in some place, in these different places, then they collapse to form black holes.
Right.
And time on the Alice's side is going this way, not this way.
Yeah.
Okay, good. So my other question, that's great. That's a good clarification. I accept that. So the other one is that I'm a little confused when you say about the number of the actual volume is expanding in this computation. I mean, I'm not sure I agree that, that computation is space-time volume, but let's accept that for the moment. But the actual volume, here's now your picture of a physical black hole. A star collapses, goes like this. It's the same Penrose diagram. Here's the singularity up here. Here's the horizon. And here's a bunch of folks who fall into this black hole, and they're going to do some kind of computation on the way in.
Okay.
And they reach the singularity in a time which for them, in their proper time, is essentially on the order of the radius of the black hole divided by the speed of light. They can only interact with, actually a relatively small fraction of the stuff that's actually falling into the black hole. So that computation is actually not expanding in time. Indeed, if you were to go and if you look at the folks that are falling to the black hole, the physical volumes up here are actually much smaller in the space-like direction than they are down here because they're closed, trapped surfaces, so they're contracting. So I don't understand what you say that I understand there's an amount of computation that goes on going into the black hole, but I don't understand what you say that you were drawing these pictures where you go like that, say, look, it's getting bigger and bigger and bigger, but that's not the computation experienced by the stuff that falls into the black hole. Can you comment on that?
Yeah, that's exactly why the volume cannot be measured. Because that's exactly why the volume can't be measured. And therefore I didn't use volume. I didn't use the value of the volume as the computation. That's what Umesh and company used as their goal, the computation, knowledge of the volume. I think for every reason, the reasons that you say, knowledge of the volume is not feelable, really. So they used another trick to make an argument. And the trick is, I think, the right trick to say, supposing the dictionary is efficient, then they prove this contradiction. But I did not use that trick. Instead of asking to compute the volume, I replaced it by computing whether it's A or B. Now, A or B come in from the left-hand side and move upward toward the right so that they do move into the region where Bob can see them. I don't have the picture in front of me, but well,
I remember it. Yeah, it was a great picture. Yeah. I mean, it's very similar to this, right? Like Bob sends in stuff right here. Here's the rest of computation. But I guess the point is these folks inside, this computation ends at the singularity, the space-like singularity, at which point they don't really have any chance to communicate with each other. So I guess my last question is, if the computation...
Well, that's it. Let me insist. That is exactly why I didn't use that as the interesting thing to try to compute.
That's
also why it was necessary to use the two-sided black hole to send in a message from the left, which would ultimately appear way up on the right-hand side, in the right-hand corner, and be accessible to Bob as he fell in.
Mm-hmm. So thanks.
Millions of questions. It's a wonderful talk. I really good. I will get in touch with you outside of this and catch up because I have many more questions after your wonderful talk. Beautifully done.
Great. Thanks, Seth. Those are great questions. I think we should move on to the panel, which everybody's waiting for quite eagerly. So if you can have the videos of the panelists pinned.
Hello, Edward.
Great. It's a real pleasure to introduce the panelists. It's an incredibly distinguished panel. So Ed, I think is he's a much decorated and legendary figure in both math and in physics. He played a central role in the development of string theory through the mid-80s, mid-90s. He's also a Fields medalist. Jeff Penington from Berkeley. Ed Witten is at the Institute for Advanced Studies. Jeff Penington from Berkeley. He did the first derivation via gravity calculation to show that black holes return information to the outside. And then Scott Aaronson, everybody here knows, I think, for all his work on computation. He's joined us as a panelist many times and speaker many times. But I think what's relevant for today is that he really is somebody who lives this computational lens on the science, on physics. So he understands, enough physics to speak meaningfully between complexity theory and physics. So really great to have all of you here, and it would be great to have your your reactions to Lenny's talk or anything you want to add in any order that you'd like.
In full disclosure, I should say that all of these people are good friends of mine. That Edward I've been interacting with and having physics discussions with for probably more than 40 years. And I've written papers with all three of them, come to think of it. Yeah. So, hi, guys.
Hi.
Lenny. Hi, Lenny. Nice talk.
Thank you. You and I have been talking about this subject.
We have been, yes.
Yeah, probably for about 5 years or something.
At least. So you want me to start?
And Jeff and I have had a lot of fun with snakes.
Yes. Yes.
Which I think actually
and their lunches, right?
Yeah, and I think it actually comes into this issue here too.
It does. But Scott, I think Scott was saying in the chat he was going to explain what he thinks JI/poly.
Yes, JI/poly. Yeah, that's not really a idiomatic naming of complexity classes, but that's okay. No, I would like to define this thing and understand what is or isn't in it. But Lenny, I was very fascinated by the history that you recounted in your talk, and especially the hidebound complexity theoretic establishment. I guess represented by me.
No, that was not,
who were politely skeptical.
Wait, Scott, that was not the message I was conveying.
No.
What I was conveying was the opposite. I thought that the physicists were a little too quick to buy into it. No, I was
okay. Well, that would be a different way to tell that story. But so Lenny and my first contact. I don't know how well you remember it, Lenny, but it was when he invited me to give a talk at the string theory seminar at Stanford in 2006. And I talked about something that I thought would be just completely radical. I didn't even know how well it would go over, right? That high energy physicists should have some knowledge of computational complexity, because if, for example, a physical theory implied that you could solve NP-complete problems with only polynomial effort, then that could be seen as an inherent problem for the theory. I
remember it extremely well.
Okay. Well, much like if it predicted, superluminal signaling or things like that, because, what people should understand is that this is not just a technical question of, solving optimization problems a little bit faster, right? This is really about automating mathematical creativity itself. Can you just find a proof of the Riemann hypothesis in ZF set theory, if such an object exists, and just, pluck it out from, the whole, space of possibilities, right? And in as, in only as much time as would be needed to write it down, right? This is the kind of thing that we're talking about. But then around 2013, 2014, probably, Lenny himself, got interested in complexity theory, and ironically became much more gung-ho about its relevance to physics than I had ever been. Right, and started saying, not just that it's relevant, but that circuit complexity is this fundamental quantity in ADS-CFT, right? And I was then in the bizarre position of saying, well, let's slow down a bit, right? How could it be a fundamental quantity, right? I mean, for one thing, there are different versions of circuit complexity. There's, with ancilla qubits, without ancilla qubits, right? If we don't even know which one, how can we pick one and, elevate it to a similar status to entropy or whatever. But I would say that by now, because of Lenny's work, because of, Harlow and Hayden and Bouland, Fefferman, Vazirani, and and Jeff Penington and a whole bunch of others, I would consider it established at this point that when you ask about how do you decode information from the Hawking radiation, about the infalling matter, right? Or when you ask, what is, how does the ADS-CFT dictionary work, right? That these questions have a complexity theoretic flavor to them, right?
Absolutely.
And that is something that is inherent. That's not just an artifact of the way that we're thinking about them right now. I mean, you can view BFV as essentially saying that. And, I guess this new argument is sort of a sharpened version of that. So now, regarding the physical plausibility of, Lenny's proposal to, sort of learn the answer to a computational problem by jumping into a black hole, and then, I guess, valuing truth about one specific computational problem, over your own life, and your ability to share that answer with anybody else, right? So, I'm going to leave it to my extremely distinguished fellow panelists to comment more, on the physical plausibility of the proposal, what about the back reaction, and would this actually work, right? What I wanted to do is comment on the, maybe a computer science aspect of this challenge to the quantum extended Church-Turing thesis, because that is what it is, right? That's what we're talking about here. Now, one of the most basic, if annoying things that we learn in computer science is that the complexity of a problem can depend radically on just how the input is given to you, right? So, let's think about Lenny's setup, right? Where, you said, you're given a quantum state, let's say of n qubits, and you want to decide whether it is random or pseudo-random. Like, let's say whether its circuit complexity is exponential in n or polynomial in n, or whether one of two shock waves was applied to it, an A or a B shock wave. We could do these different versions. Okay, and then you answer that by jumping into the black hole. Granted, if the state was maximally complex, then you'll just die at the event horizon and you'll never learn the answer. But, if it's not maximally complex, then in your last seconds before you hit the singularity, you can know. And but now, what I would like to ask is, how is the state actually given to you? Because, what I would like to know is, if this does give us power beyond what a quantum computer would give us, then how much more power? What exactly could we solve? Could we solve NP complete problems, for example? Okay, but what I found in thinking about this was that the answer depends, sort of very much on what we take the input to be. So, there were three possibilities, basically, that I see as being on the table. The first one is that the quantum state is given to you as a quantum state, just, physically, you're handed the n qubits. This was also the scenario that Bouland, Fefferman, Vazirani, considered,
yes.
right?
Yes.
And in this case, like I'm pretty convinced, at least given the assumptions and and so forth, that yes, you can learn certain properties of that quantum state that might have taken an exponentially large circuit, to learn with a standard quantum computer. But if you had access to the interior, then you could measure those things. Now, this is not, normally when we talk about the extended Church-Turing thesis, like, people didn't even bother to phrase it in terms of, well, what if the input is a quantum state? They just weren't thinking about that, right? They were thinking about problems where the input and the output are both classical. Okay, so already to have this discussion, we are generalizing what we mean by the extended Church-Turing thesis to talk about problems with quantum inputs. But okay, fine, we can do that. But you could maybe that feels a little bit less threatening for from the standpoint of NP complete problems or something. Okay, now a second possibility would be that the state is given to you as a gigantic table of amplitudes. Like, let's say 2 to the n amplitudes, right? And in that case, I'm again convinced that you would be solving something hard. The trouble is that to even create the input would then take an astronomical amount of time, right? Either that, or else we could scale it down to where 2 to the n is small, like it's polynomial, but in that case, n would be logarithmic. Right, and so we'd then be saying that the black hole would have only logarithmic size, and only a logarithmic size Bob could fit into it. So not us, presumably. Right, you have to be very microscopic to jump in and learn the answer. Now, a third possibility, maybe like the most attractive one in a way, would be that the quantum state in Lenny's problem would be described to you via a circuit to prepare that state. Okay, and in this case, you know, we get around all of those problems, right? But the trouble is that now by just examining that circuit, it might be easy to figure out, you know, just like what shock wave was applied, like whether it was the A or B shock wave. It might be just manifest if you just examine the circuit. And so in order to get a hard problem by that third route, what you would need is a way of obfuscating the quantum circuit. You would need a way of hiding the information about what shock waves were applied or in what order. And you know, whether you can do that kind of thing, I would regard as an open research problem in quantum complexity theory and quantum cryptography, you know, which, you know, people could very much think about even with no motivation from quantum gravity. Okay, but that is what the question would then be, right? You know, now I think, you know, I have only one real substantive disagreement with, one serious disagreement with what Lenny said in his talk. And this is where he talks about, well, you know, Bob is just made of qubits. And so, you know, we can just think about this whole experiment as happening, in a quantum computer. We can dispense with the actual black hole and just, you know, think about a simulated black hole, right? I mean, to me, like if that were true, then in a way it would make it less interesting, because, you know, to say that, okay, there is some basis, you know, in which you can view your quantum system, or there is some dual description of the system in which it is solving a hard problem, is actually a very weak claim, right? That is true for essentially any system, you know, as far as I can tell, right? And to me, you know, what is interesting about black holes, what is special about black holes, is that we believe, based on classical GR, based on quantum field theory, that there is this interior that someone who jumped into the black hole could actually experience. Right? You know, they couldn't tell anyone else, but at least they would have that experience. In the case of the simulation, I don't know, you know, and I'd say your guess is as good as mine.
I think quantum simulation is not all that different from the reality that it's trying to simulate.
No, these are very ancient philosophical problems.
Yeah, no, but I think more so than the classical context.
All right.
Okay.
Anyway, that was all I had to say.
Yeah,
no, that's great. Actually, thanks for that, Scott. I'd actually missed, Lenny, I'd missed your this thought that you could actually maybe even think about a quantum computer doing all this, because because then that would manifestly make it quantum computers are what we define the quantum extended Church-Turing thesis with.
Except that he's imagining this exponentially hard change of basis.
Right.
Describing the observer's experience, right?
Yes.
But that was my point. Then it's just kind of a mental thing. It's more so than a physical one.
Right. But to your point, I would say that that once we formalize the quantum extended Church-Turing thesis, there is really this choice, is it a classical input or a quantum input? And I'd view that as a relatively small issue. It's a completely acceptable thing to say, well, it's a quantum input. Yeah. But I would agree that that if you were able to move it to where the input is an obfuscated circuit, that would be sort of icing on the cake.
Yeah, I mean, I would just like to know, is nature still censoring NP-complete problems even here?
Okay,
yeah.
So
in this extreme scenario.
Yeah. So look, that is, I made my best attempt to try to define a complexity class. I do not make, and I claim that it's non-empty. I have no idea at all if it contains NP-complete problems. So it's perfectly reasonable to suppose that NP-complete problems are outside that complexity class, which I think you would like to say.
Oh, I don't know. I'd like to know.
Well, you'd probably like to say the opposite.
I'd like to know the true answer.
Yeah. But I make no claim there. I simply say this class is not empty.
Great.
Lenny, when you were discussing the BFV problem and measuring the volume, when you were discussing measuring the volume, you were saying there were two possibilities. There's one is that the quantum extended Church-Turing thesis is wrong, and the other is that the dictionary is exponentially complicated. And then it seemed like you were wanting to say that.
I was literally quoting.
That okay. I'm fine with those two possibilities. It seemed like you're wanting to say that the issue is actually the quantum Church-Turing thesis, quantum Church-Turing, extended Church-Turing thesis being wrong. Whereas I think I would want to say, and my impression from what Scott's saying is that he would also want to say that what the issue is the dictionary being exponentially complex. And maybe you can think about that in a different way in terms of a new complexity class. But fundamentally, even in the problem of Bob jumping in and he sees a shock in some state or another state, then from the pure quantum gravity description, this is just, he's measuring something simple. He's moving across and he's looking at something simple in the quantum gravity description. The interesting thing is that that's solving a tricky problem in the quantum mechanics description, but the trickiness involves switching descriptions.
Yeah. But incidentally, I don't regard all of this as a threat to the thesis. I simply regard it as a reason to want to review what the thesis means in that anytime new physics happens, you have to think how does it affect this thesis? And my own view is that the correct version of it, which is not threatened, involves observers on the outside.
So I am very, very confident in saying that the quantum extended Church-Turing thesis is false, if and only if an observer can concretely do something to learn the answer to problems that are outside of BQP. I'm confident about that. What I'm not confident about is who counts as an observer.
Okay, so
this really brings that to the fore.
Yes,
right?
yes. But what I'm saying is, if we want to retain the thesis, I think it can be retained. It simply has to be fine-tuned, and it has to be fine-tuned in this way. Mm-hmm. I don't think we want to abandon it. I don't think we want to say it was completely wrong. I think we want to understand in what sense it should be defined so that it makes sense.
I would say it comes closer to calling it into question than we have, in the sense that one has to work now to save it. One has to maybe not work as hard, but to say, look, I mean, what your example of jumping into the black hole to answer a question that you should not have been able to answer because it's exponentially hard. I mean, that's something. And so, well,
oh, yes.
Ruling it out by saying, well, you can't jump in, well, that does take some doing, right? You now have to say, well, it's a little more, the thesis is slightly more circumscribed than we would have thought earlier.
If the discussion is supposed to be about things we do in the real world, first of all, I would have thought that the gravitational version of the extended Church-Turing thesis would just say that the existence of gravity doesn't let us solve any problem that we can't solve without gravity. That seems like an economical statement.
Mm-hmm.
Now, whether this story with black holes contradicts it, the rules are not terribly clear to me. The entangled pair of black holes which are assumed is extremely hard to make. So if we're discussing something which we can do, part of doing it was creating the geometry, which was the starting point. It's not clear to me how we're supposed to do that. It seems off scale in complexity to build that.
I don't think it's that hard, but people are trying to do this in the laboratory now, create entangled computers in something like the thermal field double state to do quantum teleportation or traversable wormhole protocols.
Think about what would be involved to actually challenge. I think I will make the assertion that I think that in a laboratory built device, like you just said, it will not be possible to violate the Church-Turing hypothesis by simulating the jump in.
How would you tell if you did or you didn't?
I'm saying that nobody will succeed in solving an intractably complex problem with the devices you just described. I'm not making.
The trouble is that if they do, then they can't tell anyone about it.
Yeah.
I agree with you, Edward. I don't think anybody.
You won't be able to find anything you'll interpret that way.
No, I don't know that that's right. I think it will just take a long time to tell. I think using various versions of quantum teleportation and traversable wormhole protocols and so forth, it will be possible to tell what happened inside the black hole. It will simply take a long time.
I didn't say it won't be possible to answer a question like that. I just said that you're simply describing an algorithm you make from qubits. So by definition, you won't be doing anything you couldn't. I said, my assertion at the beginning was that you can't do anything that you can't do without gravity.
Yeah.
And describing a machine that doesn't use gravity in an essential way. So you're not going to contradict what I said.
No, I'm not contradicting what you said. I'm agreeing with it. But
I gave a formulation of the gravitational Church-Turing hypothesis, thesis, which was that gravity doesn't enable you to do anything you can't do without gravity. And,
unless you're willing to jump into the black hole.
Well, then we had to discuss what was the setup where you did the jumping. And you suggested a setup where gravity had not played an essential role in creating it, namely the laboratory-based qubit system. So
I would say that system has gravity just as much as any.
Well,
I think we should.
I'm asserting that that's okay. As a tautology, therefore, that system can't do anything that you can't do without gravity.
Indeed.
So just to understand, you're sort of formulating the principle which as saying we cannot, in the outside of the black hole, we wouldn't be able to solve any problem faster than with gravity than without, or some not much faster. And
yes,
is that okay? No,
let's say for the weak interactions, the weak interaction extended Church-Turing thesis says that the existence of weak interactions don't let you solve problems you can't solve otherwise.
Mm-hmm. Yeah,
I don't think we're disagreeing, Edward. I think we're completely agreeing that a correct formulation should simply say that you can't do anything using gravity that you can't do without it. But you need to make that correct.
There is a question, I think that is a real question. Say you're given some simply describable classical problem, say an NP hard problem, but it doesn't have to be, but something that is not in BQP. Can jumping into a black hole somehow help me solve that problem, and such that I will know the classical answer to that decision problem, 1 or 0, for some small amount of time, and then I hit the singularity and I die, and the problem remains unknown to the universe? It seems to me that the answer to that question is almost certainly no. Like it would be very, very, very surprising to me if the answer to that question was yes, that jumping into the black hole let you see something that you couldn't otherwise do.
Okay, so you've now committed yourself to saying no to something which I claim to have exhibited can be done.
I'm saying this is for a decision problem, like a classical decision problem that is not in BQP. So the problem is phrased in terms of, I'm told some classical question, say, what are the prime factors of, well, that's not a good one because I can do it in BQP, but something harder, some 3-sat thing or something like that, maybe. I claim that if that problem is not in BQP, then I also won't be able to find out the answer to it, even if I jump into a black hole.
So Geoffrey, I mean, if my obfuscated circuit proposal worked, then would you count that as an affirmative answer to that question?
Let's see. So I'm somehow phrased.
So I give you a circuit, which in some obfuscated form either prepares a state, of a black hole or the CFT dual of such a state that had an A shock wave applied, or else it prepares the state that has the B shock wave applied, right? But again, not via some obvious path. And then examining that circuit, maybe it would take me exponential time to figure out whether it was an A or B shock wave, if the obfuscation scheme was a good one. And yet by jumping into the black hole in my last seconds, I could see the answer to that. I mean, would you
I would consider that a contradiction to what I just said. I'm not ruling out that as possible because who knows? But I think that would be,
I feel like that is That is the question that's upon us now. So I mean, I wanted to ask Ed. I mean, like I was also not impressed by the idea of like a constructed or hypothetical observer in a simulation seeing the answer to this problem, right? But what about the scenario with an actual physical black hole? I mean, would you, if that infalling observer in their last seconds saw the answer to this problem, I mean, first of all, would you see that as plausible, and would you even see that as a meaningful question to ask, whether they did or they didn't?
Well, I find it somewhat plausible and possibly meaningful. I'm sorry to hedge a little bit with those qualifications, but the setup is extremely difficult to make. That's what I said.
Oh yes, absolutely. I mean, making an ordinary quantum computer is proving hard enough. I wouldn't expect this to be rolling off the shelves anytime soon.
But I think making the system to begin with is sort of part of the overhead that we just assume is there, and then the question is, how much harder is it?
Yeah.
So I was
part of the overhead.
It's very hard to know exactly what's there. In other words, if you need exponential precision in knowing what's there, and given that exponential precision, it's easy to do something. That seems a little bit artificial. If I go back to the statement that gravity doesn't let us do something we can't do without gravity, then we have to take into account the difficulty of making the apparatus that we're supposed to use to do the computation. Especially if it's a single-use apparatus.
Well, whatever the difficulty is in making the apparatus, we can ask, given that difficulty and given that we did it, how hard is it to accomplish the task we're trying to accomplish? And there are two different answers. One comes from jumping into the black hole. The other comes from looking at quantum complexity.
Well, I think you should compare quantum complexity to the combined complexity of building the entangled pair of black holes and then jumping in.
I mean, there was a ton of objection to quantum computing itself in the early days, along the lines of, well, you won't be able to make the apparatus, right? Or it will require exponentially precise control, right? And that was a plausible view a priori, and it was ultimately, I would say, only really answered by the theory of quantum error correction, right? It's by very non-trivial schemes. Of course, it will only really be answered by the actual building of the devices that implement the theory. But
in this discussion, Lenny needs much more than a quantum computer. He needs a quantum computer whose functioning depends essentially on gravity.
Yes.
Functioning does not depend on gravity.
Right. So I think the question that one could now start researching is there some analog of fault tolerance for gravitational or black hole computers? Where you would be able to detect and correct small errors. That would be the practical question, so to speak.
I think even if we accept that we can do these things with no errors, then to focus on Scott's circuit set up for the problem, but we can certainly make an obfuscated circuit that is exponentially long. It's some exponentially long way of preparing some state that actually has some simply observable thing, but you can't tell what that thing is because it's just some horribly obfuscated thing. And then you could imagine, from Lenny's point of view, we ignore the costs of carrying out the instructions of doing that circuit. That will take us an exponentially long time, but we assume we get to do that for free. And then we ask, how much time does it then take us to figure out the problem? And by jumping in, we can find the answer essentially immediately. This is a physical black hole. If we're not allowed to jump in, then we're still sort of at square one, or it will still take us a long time to do from the outside. But I think that's sort of a very different problem from if you could have some efficient obfuscated circuit where there would really be, something that could efficiently be done by jumping in, a classical problem. The problem is completely phrased in classical terms and it has an answer in classical terms, classical decision problem that you could solve by jumping in and you couldn't otherwise.
But then
have that.
Yeah, I understand what you're saying. I think, I don't know if I agree with it or not, but you are asking now about the boundaries of this complexity class. You're asking whether it actually includes any interesting computations that could actually be done inside and I don't know.
So if I can say, you know, there are two things here, it seems to me. One is, at this stage, you know, surely we should be, I mean, we can think of all these as thought experiments without saying, okay, you know, can we carry them out in principle as opposed to how hard it would be to do it in practical terms. But secondly, you know, in terms of, Jeff, in terms of, you know, creating this obfuscated circuit for this state, and then of course one wants to create it somehow homomorphically so that now the state can be acted on homomorphically by the shock waves that are coming in. So you fall in with this classical description, and then you act on this hidden quantum state, and you eventually end up answering this question, you know, that you really wanted to, by saying, okay, now what's the volume or something.
Yeah, I think my objection can be phrased as follows. In quantum field theory, we think the quantum extended Church-Turing thesis is true. You know, Lenny made possible contradictions with that, but let's assume that's the case. Then, assuming everything we do in the quantum gravity theory is well described by quantum field theory in a semi-classical background, then it also shouldn't be able to break the quantum Church-Turing thesis. So it seems we either need to be given as part of the problem a quantum state that has a non-trivial holographic dual, and so some non-trivial trivial geometry that we didn't make from scratch. That's the case in Lenny's setup. Or we need to somehow make that semi-classical evolution break down. I would say from what we know about quantum gravity, to make the latter happen, we either need like Planckian curvature, or we need exponential complexity, like exponential time, exponential number of things getting involved. I don't think there's any other. I think it would be very problematic for semi-classical space-time if we could make it break down without either of those conditions being true. So that's why I'm inclined to say that this shouldn't let us answer any classical decision problems more efficiently.
By answer it now, you are including the possibility of jumping in and answering it.
Yeah, I will allow you to jump in, but the problem itself is just phrased as some short classical description of the problem. For example, here's a quantum circuit. And then does that quantum circuit have, you know, which of two states it does?
Okay, so how does the AB problem why is that not an example?
I would say that's not an example because you have to be given a quantum state, not just some classical problem. You have to be given some quantum state, and one that's a holographic quantum state that you're then allowed to jump into the.
Is this a distinction that Scott was addressing?
I think it's the distinction between his first possibility and his third possibility, basically.
But Geoffrey, I mean, why not treat the preparation of the holographic state as just, you know, an engineering cost, you know, analogous to building the quantum computer, you know,
yes,
albeit a billion times harder or whatever.
So are you meaning building it on some quantum computer or?
No. I mean, again, like I am viewing here to the principle that, you know, you can't draw blood from a stone, or, you know, or like change the computational model just by thinking about something in a different way, right?
So we'd have to make physical black holes. Yeah,
you need some actual physical resource that will solve a problem, you know, that beyond what a quantum computer can solve. And the question is simply, you know, are black holes such a resource or not?
My claim, and I don't have much evidence to this beyond I don't think you can make semi-classical gravity break down without either Planckian curvature or exponential times, is that there shouldn't be anything you can do to make that. Like,
sorry, where did any of this involve semi-classical gravity breaking down? I certainly didn't assume that.
If semi-classical gravity doesn't break down, and I just start with some Cauchy slice, and I can just evolve that Cauchy slice to the future, and the quantum fields just evolve in some way, that seems to me that it's efficiently simulable. Like with perturbative back reaction on the geometry from having large amount of mass, that just explicitly, if QFT is efficiently simulable on a quantum computer, then semi-classical gravity doesn't seem any harder to just evolve the state forward in time. In your case, it would mean starting from a Cauchy slice, where there's this shock on the left, and then you evolve forwards in time, and then that shock falls into the black hole. But at the early time, you already have the shock on the left in that Cauchy slice. So it's a simple thing from the point of view of the quantum gravity system. It starts simple and it remains simple.
So wouldn't that be saying that your semi-classical gravity approximation for such instances would not hold? And is there anything wrong with that?
I think if you create two black holes by collapsing them with some qubits, and then you somehow manage to turn that into a classical Einstein-Rosen bridge, that would be an example of something non-semi-classical happening. Because semi-classically, you just end up with two black holes with a load of entangled particles sitting inside them. But to turn that state into an actual thermal field double state that actually has a classical wormhole, short classical wormhole, seems hard to me. While remaining inside the system, like.
But isn't it possible that your semi-classical approximation breaks down in other ways than that? I mean, that you haven't thought about so far. I mean, we could start with a computational problem that's hard.
But I think Lenny's suggestion is a qualitatively different. It's the difference between what an observer just in the quantum gravity theory can do and what problems they can solve if they're handed a problem, versus what I can do if I'm handed a holographic quantum system and then allowed to jump into it versus not being allowed to jump into it. And I totally agree that the latter, then there's things can be simple if you can jump in, but hard if you can't jump in. But I would have said that's about the complexity of the dictionary going between the two sides.
Yes.
Versus, yeah. I don't think I think this is a matter of wording. I don't think I totally agree with the basic story you're giving.
Good.
Great. Let's see. We've run pretty long. It's been an incredibly stimulating discussion. I just wanted to give I don't know. See if anybody on the panel had anything else to say. Ed, for example, did you have any final words?
Not really. I think I'm satisfied with the discussion.
Great. Great. Well, thanks again, Lenny, for a fantastic talk, and thanks to the panelists. This was a really, very vigorous, very interesting discussion, and really quite a way to end our colloquium series for this semester. So thanks everybody for attending, and see you all in the fall.
Thank you.
Thank you.
Bye-bye, everybody.
Yeah, thank you. Thanks, everyone.
Thanks all.
Okay, and thanks, Lenny. And thanks, Umesh. Okay, bye.